So, you are welcome to this to the first seminar series of the year 2026, and we are starting off this seminar today with the topic numerical solution of an associated Fokker-Planck equation for uncertainty quantification in rainfall runoff systems. And our lecturer today is no other person but Dr. Ezéckiel Sianou from the Department of Mathematics, Pan-African University, Nairobi, Kenya. The speaker received his PhD from the Pan-African University in December 2025 with an expertise in computational mathematics, hydrological modeling, stochastic modeling, and hybrid physics AI methods. His research focuses on advancing hydrological modeling through stochastic dynamics and hybrid approaches integrating machine learning. His work has led to methodological developments that support the anticipation of floods and droughts and the planning of water resources. He has presented his research at international seminars and shared his findings with the Africlimate AI community. Mr. Ezéckiel, you can take it up from there. Thank you very much for honoring my invitation.
Okay, thank you very much, Dr. Julius, for this invitation. So, and also thank you for the presentation. I'm happy today to share with you one of or a part of my PhD research work, which is about numerical simulation of an associated Fokker-Planck equation for uncertainty quantification in rainfall runoff system. So this is basically the content of the presentation. After a short introduction, we will talk about the different methods that are used, and we go to the method application and conclude the presentation. So, as it is written in the topic, rainfall runoff. What do we mean by rainfall runoff? So, you can see here that we have two different words. We have rainfall and we also have runoff. Now, rainfall is refers to a set of precipitation and that water that comes from atmosphere. So all of us, I know that we know what we call runoff. Now, what is this figure showing us? It is sorry, I just have you seen the message? I don't know if it is okay. Please, is it okay?
Yes, it is, sir.
Yes,
Okay,
it is,
okay.
sir.
Thank you. So this figure shows all the mechanisms that we have after it rains. Because when water comes from atmosphere, we have three possibilities for that water. The first one is that the water will seep into the ground. That is the first one. The second one is that water, a part of the water will be transpired or evaporated, like the trees or even the sun can remove a part of the water. That is what we call evapotranspiration. Now, the third one is the amount of the water that flows over the land. And all that mechanism together leads to the final amount of water that flows into a river. So this is basically a kind of modeling where we are going to use different model to determine the amount of water that will flow or that flow into a river after it rains. So why is it important? As you can see here, it is very important because first of all, we have so many extreme events today, such as flood and drought. So it is very important to prevent that kind of situation by focusing them over like what will happen after so many days. We can be able to use a mathematical model to predict that in order to prevent that kind of situation. It is also important to manage water resources. As you know, water is really related to so many fields today, such as agriculture, even environment, and we need to manage that different system in order to preserve our environment, even the agriculture field. So it is also important to design infrastructure such as dams, reservoir, and drainage stage. It is very important to assess the effect of land use and climate change on water availability. And it is important to support environmental conservation and ecosystem management. So now we have different type of models that are used for this kind of modeling. So it is similar like for people who are working in health or energy, any other field, where we have deterministic and also stochastic models. Now, in this field, most of models that are used are deterministic. We don't have a lot of stochastic model, especially stochastic model that are based on stochastic differential equation. So what is the main difference between deterministic model and stochastic model? The output of stochastic model can never be the same. Anytime you simulate your stochastic model, the output is always different. Even when we use the same input, you have different output. What is the opposite for the deterministic model? Because you always have the same output for any deterministic model. Now, the randomness is, we don't have randomness in a deterministic model, and it is the opposite in the case of stochastic model. The uncertainty is accounted when it comes to stochastic model. And when we talk about complexity, like it is very simple to simulate a deterministic model compared to stochastic model. Yeah, but we are going to see some kind of simulation later in this presentation. So these are some difference that we have between stochastic and deterministic model, because our work is really focused on stochastic approach for rainfall runoff. Now, the objective of this study, it is already published, this work that I'm presenting, but the objective are basically what we have here. The first one is to develop a stochastic differential equation to represent uncertainty in rainfall runoff system. The second one is to derive the associated Fokker-Planck equation. And the third one is to solve that Fokker-Planck equation to obtain time-dependent runoff distribution. Another way to call runoff is also discharge or stream flow. So the last one is to use or to take part of that numerical solution from the Fokker-Planck equation and apply now an integration method in order to compute the uncertainty over time that we will use as predictive uncertainty for rainfall runoff system. Now, the framework that we use is what we call stochastic differential equation and Fokker-Planck approach. These two equations, as we can see here, the equation 1 here is a stochastic differential equation. The equation 2 here is the general form of the Kolmogorov-Fokker-Planck equation, as you can see. Now, these two equations are related. Once you have the first equation, you can derive the second equation. Once you also have the second equation, you can go back and derive the first equation. They are really related because the second one is like a response for the first equation. Now, the S of t here is a stochastic process. That is, which is the solution of the equation 1. Now, this stochastic process is characterized by a probability density function, because the solution of any stochastic differential equation can be considered as a Markov chain. And then any Markov chain is characterized by a probability density function. Now, that probability density function satisfies this equation 2, which is a PDE, called Fokker-Planck equation. So this is basically what this framework is saying: stochastic differential equation and Fokker-Planck equation. Now, this is the model that we formulated in our study. As you can see, the equation 5 is our stochastic differential equation, but that equation was derived from another ordinary differential equation that we call hydrological model based on the least action principle, HIMOLAP, which is another differential equation used to model runoff dynamic based on using methodological data. So like we have two different inputs, precipitation and evapotranspiration. And now from that methodological data, we try to use the equation 3 to simulate runoff, which is stream flow in another words. Now we base on this equation 3 and we formulated the equation 5. The equation 4 here, what we see here is just used to fit that equation 3 because we have the S of t here in our equation 3, but that S of t is computed using the equation 4, as you can see. Now, how did we derive this equation in order to match the data that we have? Because we cannot just formulate a differential, a model, because the model cannot work, can work or can not also work. So it is really needed to be careful about how we derive the model, especially in the case of real world application, because we will show some application at the end of the presentation with real data. Now we enumerated some assumption, and one of them is that the uncertainty at each time t depends on the state of the system. And what do we mean by that? Like if you have high values of runoff or meteorological data are characterized by flood situation, a lot of water. Yeah, high values, we refer that as a lot of water. So that kind of value can create flood situation, and very low values can create drought. So the uncertainty in the case of high values must be different from the uncertainty in the case of low values. That is why we are using multiplicative noise here, because it is possible to, we have so many ways to define a stochastic differential equation, especially the the term that incorporate the randomness in the system. What we have here is normally the equation 3 exactly, the ordinary differential equation. So the last part in blue is what we added. So by doing this, we define the diffusion, which is this term, and then we have here the noise. Another way to say it, we have the standard Brownell motion that we consider in our study, because we assume that the uncertainty follow Gaussian distribution. So with all that assumption, we were able to formulate the equation 5, which is the stochastic differential equation that we use to account for both the dynamic of runoff and also the different uncertainties in the rainfall runoff system. So after that, we used a method that we call generalized method of moment to estimate the parameters of our stochastic differential equation. And this method includes two steps. The first step is the estimation of the drift term, which is the first part, as I said before here, which is basically the calibration of this ordinary differential equation. Now, we use an heuristic method to do that. We are not going to talk about it here, but after using that heuristic method to estimate the parameters of the deterministic part of the system, we got the estimated parameters that are mu and lambda. And then we applied now the generalized method of moment in order to get the diffusion parameter, which is sigma, because we have generally three parameters, which are mu, lambda, and sigma here, as you can see. Now, I think this is very simple to understand. For the second step, the equation 6 shows the use of Maruyama discretization method that we apply to the stochastic differential equation. The drift term here is exactly what we have here. So this is the blue part. Now as we use the daily time step because we have daily data. Now we use daily time step to discretize our stochastic differential equation, and the scheme is shown by equation 6. Now we square each part of the stochastic of the no, first we remove this part and we put it here. We create this difference which will be equal to the random part, like the part that shows the diffusion part. Yeah, I can also see that the diffusion part here. So we try to take the square of each part. That is what we define by LS here. LS. Now, taking the square of this part will help us to say, okay, LS will be equal to sigma square, Q square, and this variation also square. Now, this is one of the properties of stochastic Brownian motion. The expectation of the variation of or the expectation of the square of the variation of a Brownian motion is equal to the variation of t, as you can see here. And by using this, we were able to estimate our sigma, which is given by the equation 9. So basically, this GMM method or generalized method of moment employed normally. So many, or I can say two main method. The first one is Maruyama discretization method, and the second one is this property that we have here, which is a property of stochastic Brownian motion. I don't know, people who are interested or people who know more about stochastic process, they really know this kind of property. So how do we simulate a stochastic differential equation? We have a method that we call Monte Carlo simulation. It is just a method that is based on multiple simulation. As I said before that, a deterministic model, for simulating deterministic model, it is very simple. But for a stochastic model, like we can generate now so many values for the same day, because anytime you run your stochastic model, you get different value and different possible value. Now, Monte Carlo simulation help now to, based on that different values that can be generated, to compute some statistic. And this is a method that is really used, especially in stochastic modeling. Now, the first step is to discretize the stochastic differential equation as sorry. So the first step is to discretize the stochastic differential equation as shown by the equation 10. And the second thing to do is to apply the Monte Carlo method. First, we generate multiple stochastic trajectories from the stochastic differential equation, and then we can be able now to estimate statistics, such as mean trajectory, different quantile, even probability density function that we call PDF here, predictive interval, and so on. Now, the issue with this method is that if we cannot be able to simulate a lot of values, we cannot also be able to derive a more complete and a very true probability density function. Now, because the Monte Carlo simulation needs to simulate a lot of values, but because of computational resources and because of some method that will be used, maybe the method will not be accurate, those stuff, it will be very complicated to say that we can have a PDF or a probability density function that will really be what we want. It can only be an approximation with some gaps. So in order to solve that issue, that is where the Fokker-Planck equation is important, because that one can just help to get the full distribution and a more complete distribution of the probability, a more complete distribution, as you can see here. So now the Fokker-Planck equation will help us to get the PDF that will normally be estimated using Monte Carlo simulation, and it can be something that is not that correct, because of the method that we use. Now, by using the Fokker-Planck equation, we can be able to get a very stable and very complete, and even a distribution that can show the Q properly compared to the Monte Carlo simulation. So from there, we were able to formulate our Fokker-Planck equation, because this is the main goal of the work. After formulating the model, the stochastic differential equation, we need to derive the Fokker-Planck equation and solve that Fokker-Planck equation, because the solution of the Fokker-Planck equation is what is important for us at the end of the day, because that is what we will base on in order to do what we call uncertainty quantification. So we try to let F, which is equal to the drift term, and then the G that you have here, which is equal to the diffusion term of our stochastic differential equation. So from our stochastic differential equation, we were able to derive this equation 11, which is called Fokker-Planck equation. You see the F here, which is here in blue, is the drift term of the stochastic differential equation, and G that we have here is the diffusion term of the stochastic differential equation. So this equation is a PDE, and it will help now to derive or to compute or to determine the probability density function that is the one for the solution of the stochastic differential equation. Now, these are the initial and boundary conditions. As you can see, the way we got it is more detailed in the paper. I think I'm not going to talk more about this here, but these are used when we were implementing the Fokker-Planck equation in order to get the solution. Now, we use a method that we call adaptive implicit finite difference methods. And the reason why the word adaptive is here is that, we can just use we can say implicit finite difference method, but we started with this implicit finite difference method, and we got a lot of instability. The result was not unstable. Also, this solution didn't converge because of some constraints that the Fokker-Planck equation in our case showed. That is why we opted for the adaptive implicit finite difference method. Now, the temporal derivative was just discretized using a forward unwind scheme as shown by the equation 14 here. This is simple. It is a first order approximation, as you can see here, and the diffusive term is discretized by using a central approximation of order 2, as you can see here. This is also something that most of us we know here. I can say it is an order 2 approximation. Now the main issue is this first part, which is the convective term. This is done with a first order and approximation method, and this one was discretized using a second order approximation method. Now this convective term is what created some issues, and we will talk about it. How to deal with the convective term? Yes. This equation looks a bit like the advection diffusion equation. For those who are in fluid mechanics, then really they are really familiar with this advection diffusion equation. And before solving the advection diffusion equation, it is important to know the direction of the flow of to think about the velocity. Yeah, because it can be positive or negative. And that velocity in our case is we can it is what we call F here, because the F times the P is always positive. Now the F can be negative or positive, especially because of the methodological data. Now we need a method that will be adaptive, that will consider the sign of F at every day. Like for each for each time, we need to use a method that will automatically detect the sign of F in order to make the approximation. Now, when F is positive, we use a backward upward scheme, which is given by equation 16. When it is negative, we use a forward upward scheme, which is given by the equation 17. And from that two equation 16 and 17, we were able to build the equation 18, which is the discretization of the convective term. Now, as you can see here, we use this mass and mean in order to manage this case of positivity and negativity. For this part, this corresponds to the first equation, which is the equation 16. Because if F is positive, we see this will be equal to 0, and we will only consider this. So if F is negative, the first part will be 0, and the numerical scheme will only consider this. So it is something that will automatically be considered based on the sign of F. So that is how we deal with the convective term in order to ensure a more stable scheme that we finally implemented. So combining the discretization of the temporal derivative, the convective term, and also the last term, which is the diffusive term, we were able now to obtain the equation 20. This equation 20 is the numerical scheme of our Fokker-Planck equation in our study. And now the implementation needed to solve a matrix system of in the form of A times P equal to B. A is a matrix that will derive from this scheme. P is the probability density function, which is the solution we are looking for, and B is also obtained from that equation 20. So we solve this through implementation, and then we got the solution of P for each T. Now, after getting the solution, as I said at the beginning, or I don't know, not the beginning, but somewhere, what is important for people in hydrology is the result. Like after doing all that mathematics, and we get now, and after getting that numerical simulation, which is the solution of the Fokker-Planck equation, because there will be form of like curve. Now, what is important is to take part of that solution to build now uncertainty as prediction, and that uncertainty is what is really useful for them in order to prevent any flood situation or drought situation, or in order to do anything that they want. So in order to take part of that numerical solution of the Fokker-Planck equation, we employed here a method that we call composite Simpson 1/3 rule for integration, because the uncertainty quantification in our study meant to evaluate the most probable region under the curve, which is under the solution of the Fokker-Planck equation. And in order to evaluate that, we need to compute the integral, because we know one of the property of a probability density function is that the full integral is equal to 1. Now, our case, we don't want to compute the full integral because we already know that full integral, which is equal to 1. Now, we need to do some restriction by choosing some part of the area under the solution of the Fokker-Planck equation and compute numerically that integral. And in order to do that, we employ this composite Simpson 1/3 rule, which is given by the equation 21. So it is 4 other approximation methods. And yeah, for any case you are using real world data, it is important to evaluate your model performance. And this matrix that you have here, NSC, which is another way to call it, is Nash metric. And the second one is RMSE, root mean square error. So these two metrics help to know if we have a good model. The model is working properly, or the model fits better or fits well with data that we have in front of us. And the mathematical value formula are shown here. For the first one, the optimal value is 1, and the second one, the optimal value is 0. So this matrix help us to be convinced that the model that we've developed can really be used to model real world data. Now, this is the application part of all that method that we have just presented. As I said, the goal of rainfall runoff is to simulate water that will flow into a river now from meteorological data. In our case, the model that we have, because we have so many meteorological data, but in our case, we have precipitation data, and also we have potential evaporation data, which are in black here. The first two lines, the first one is precipitation or rainfall, if you can see it, and the second one is evaporation, potential evaporation, that we call PET in our case. So we use the model now to use these two black data to simulate or to generate the third line. Yes, this is what we did. Now, after solving the Fokker-Planck equation for some days, we try to plot the solution, as you can see here in figure 3. So we just plotted we have some solution of the Fokker-Planck equation here, as you can see, for some days. Yes, now this is where we employ the Simpson methods, because as I said, if you want to consider the full area under the curve here, it will be equal to 1, which is one of the property of a probability density function, because our curve here is a probability density, the one of a probability density function. So for us, we were more interested in a method that we call high probability region, which is a way to define the most probable region under that probability density function. And that most probable region is what will help us to build our uncertainty range. Q here is what we call uncertainty quantification, because that is the main goal. So what we did is just what I said. We used the composite Simpson method to do that. And this is just for 1 day, as you can see here. And we also have some, like, they observe, after doing that, we have that the observe value for that day. It belongs to the interval that we built. Also, the expected value is in red here. And also we have the different bound, as you can see. Now, this is the consequence of what we have here. This figure here is for 2 years. We built that uncertainty range for 2 years, and we have in red the expected value of the stochastic differential equation, which is the prediction, the point prediction. And in gray here we have the uncertainty around the prediction. And this is basically the end of the presentation. So we have developed here in this study a Gaussian-driven stochastic differential equation, and also we derived the associated Fokker-Planck equation, which are two new models that we developed for rainfall runoff system. Now the model was calibrated and estimated. The parameters were estimated in order to reformulate the Fokker-Planck equation, and we solved that Fokker-Planck equation using an adaptive implicit finite difference methods. And then after that, we obtain the probability density curve that we use now to build the uncertainty or to predict the uncertainty in the rainfall runoff system by employing the composite Simpson 1/3 rule. And this framework provides a stable runoff PDF simulation and a clear methodology for uncertainty prediction in rainfall runoff system, which is even the first time to employ probability density function with this method. The high probability region method that is derived using the Simpson method to build uncertainty quantification. So these are some references. As you can see here, the third references here is the reference of the paper from this work. And thank you for your attention. Thank you. If you have any question,
Thank you. Thank you very
you can
much.
ask. Thank you. Yeah.
Thank you very much, Dr. Ezéckiel, for your very wonderful and interesting lectures and seminar. I am sure that this particular topic you have given would have opened a lot of insights and would have inspired some of our participants in this seminar. So I would like to throw the floor open for comments and questions. Please, let's take it very short, please. Comments, thank you. So just use the react button and raise up your hands. I'll call you.
Okay.
Comments. Any comments for the lecturer? Or questions, if you have? Okay, I think somebody put a question in the chat box. Somebody was asking, what is the probability flow? I guess
okay. Okay, let me see.
Maybe the person was trying to get as a PDF, probability flow.
No, it is just the PDF.
Just the PDF, exactly.
Yeah.
Any other question?
Yes, can you hear me? I have a short question, please. Can you hear me?
Yeah.
Yes.
Okay.
Yes.
Thank you. Thank you, Dr. Sianou, for your speech. It was very interesting. I'm not familiar with the field, but I was very surprised by the method you used to identify lambda and mu. I think there is a problem of identifiability because it's not easy to have the real value of lambda and mu at the same time.
Okay. Yeah. Yes. So, is it a question?
Yes, it's a question. How do you manage the problem of identifiability?
In our case,
going back to question one, to the first question, yes.
Question one. What is it? The question one is.
No, it's not that one. No. Maybe excuse me. Yes, equation
okay.
3, please. Equation 3, yes.
Okay.
I think that is not easy to have the real value of mu and lambda at the
Mhm.
same time, because you have to solve the problem of non-identifiability.
Yes, that is a very good question, because this kind of problem is something that we see every time today, especially in the field of hydrology for more complex model. Now, the method that we use here is a method that we can call a random method, like we call it heuristic method, optimization method. We first define a wide range for each of these two values, and we randomly select or randomly pick values from that range. And after picking that value from that range, we simulate the model using that values that we pick from the range for each of the parameters. Now we repeat this same operation, and by the same time we try to reduce the interval or the range. So how do we know that the value that we are picking from the range are are good for our model, or are the parameter that we are looking for? We use the metric that we have here. So for each couple of value, we try to compute the metric here and try to like, if I assume that we have the RMSE as the objective function. So for if each couple of parameters, we simulate the model, and then we compare that value of RMSE to the previous one. So the goal finally is to optimize this RMSE, which will basically be to retain the parameters that will give the smallest value of RMSE. So that is how we did it. But that is what we did for this study. There is another study that we have done recently, and we find an optimization method that we give directly the values of the parameter without even using this heuristic method. I don't know if it's okay.
Okay, thank you.
You're welcome. Yeah.
Okay, that means that means the parameters lambda and nu are not unique.
They are unique, I can say, but because for the optimization method that we have used now, when you employ the method is called Nelder something. Now it gives you directly unique couple of value. It is possible that, okay, we can also find different set of value of parameters value that we also give you some good simulation, but it gives you the best simulation that you can get. That's why I can say that these values are unique in terms of the values that we help to get the best simulation of your model based on the data that you have.
Okay, thank you, thank you, thank
You're
you.
welcome.
Any other question? Okay, if there's no question, maybe I just ask a very simple question. I don't know, Dr. Ezéckiel, is there any scenario where memory can be useful in your work? Maybe from a day's if a day's data may affect the next day's data, maybe something like that. Maybe memory. Then you have like some memory effect. Because the reason why I'm asking is, we have like the fractional operator, like, when you have like fractional operator that can take care of memory effect. So if you can relate this your study to the fractional Fokker-Planck equation. I don't think if you can.
Okay, I understand the question now. So for this work, there is no memory.
Yeah, I
But
know.
there is
I'm just saying maybe a way you can extend. Maybe if you can, maybe you want to just, consider another
yeah.
application, yes, of
Yes.
looking at how
So
you
I can
can.
go to the stochastic differential equation that we have here. This equation, yes, the stochastic differential equation here.
Yeah.
We consider the standard Brownian motion here, which is the WT. So we can consider also the memory, as you said. which mean so many different things such as asymmetry of the distribution or even the heavy tail of the distribution. Those
Yeah.
characteristics are not considered here. Now we can change this Brownian motion by a Levy
Heavy, yeah.
distribution that will allow us now to get a fractional Fokker-Planck equation.
Excellent. Yeah.
So in that case, we are talking about the memory as you said.
Yeah,
So
yeah.
it will be a bit different.
I
But
think
mhm.
it's a very good direction you can also look at.
Yeah, yes. There is one of our work that is about that,
Oh, okay.
and maybe you can check about it.
Okay, thank you so much. Okay,
You're
so
welcome.
thank you very much for coming to this seminar, and I believe that this talk would have inspired or motivated you. For those of you working in the area of numerical analysis, these are areas where you can also explore, and if you want to also discuss with the lecturer, Dr. Ezekiel, I don't know if you can type your email at the chat box.
Yes, sure.
Please. So if you want to, discuss with the lecturer and maybe you feel like you want to work in this area, you can send him an email, and I'm sure he will respond to assist you with the necessary materials that you can use to start working in this area. And yeah, so the email is there. You can copy the email now because we're about to close the session. So next month, we'll be having the next seminar series. I don't know. Dr. Mukaila, are you here? Is Mukaila still here?
Yes, I'm here.
Yeah.
Doctor.
So are you, Dr. Mukaila, will you be ready to give us your seminar next month?
When is it? Is it next month?
Next month, in the third week next month.
Yeah, I'll be in Ghana, so I'm really sure I'll be available.
Okay, yeah, we keep talking.
Yes, but I'm sure
Okay.
I'll be available.
Okay, nice. Okay, so I'll just let one of my mentors to just give a word of advice to us or something before we leave. Professor Lekunle, I don't know if you are there. Is Prof still here with us?
Maybe it's not
Professor
there.
Lekunle, okay, maybe he's not there. Okay, all right. Okay, so we thank you for witnessing this seminar series, and I wish you well in your research, and I say bye-bye.
Thank
you, Ezekiel, for your wonderful lectures. I really appreciate you. Thank you so much.
you, Data.
Yeah, bye.